Last but not least, we're going to hear from Shirley Brosmeyer about core parts.
Hi, thanks for your time today. I'm going to start with the bottom line up front. We at Core Parts are planning to add a ceramic thermal barrier coating to the hot gas sections of small turbine engines, those under 1,000 pounds of thrust that power missiles and unmanned vehicles. This addition of the coating is going to allow an augmentation of the thrust by 20% because the temperature that one can run is about 300 degrees higher in the hot section. You can see a picture of the type of blisk that we're talking about. It costs about $10,000 as a baseline, and for $1,000 more, we can add this coating, which is worth about $20,000 an engine, because the alternative is to scale up the engine to get the kind of thrust that we're talking about. The Air Force's S&T 2030 strategy calls for complexity, unpredictability, and mass to counter our current adversaries like China and Russia. And some of these systems you can see on this chart are being used in that capacity. The propulsion systems for small unmanned vehicles has not gotten the attention that the larger engines have gotten over the last decades, and larger engine technologies such as thermal barrier coatings can be very helpful for the small turbine class. The estimated military market is about $5,000 per year in this size class, and the propulsion costs about 30% of the system, or $25,000 to $200,000. The picture on the left of this slide is not a small turbine, but it does illustrate the hot section that we're talking about using the coatings in. The hotter you can get that area, the more you can get out of the engines. The chart on the right shows 3 examples of blisks that could be used in such a turbine area. The one in the bottom left is an uncooled blisk that costs about $5,000. But doubling the price, one can add cooling to that blisk and get a 15% thrust increase. Once one has done that, it's extremely compelling to coat that blisk to add another 20% of thrust for only an additional $1,000. And that's what we intend to do. This chart shows how a thermal barrier coating works. The schematics are meant to represent a cross-section through the hot wall of a turbine airfoil. The one on the right has a thermal barrier coating, and much like the insulation of your house, it protects the metal wall from seeing the hot gas. You can see that for the same metal temperature of these 2 schematics of the walls, the one on the right has a much higher gas temperature allowable. This is how the coating is going to allow a 300-degree increase in the hot gas temperatures. These coatings have been used quite a bit in large industrial turbines as well as aircraft engines, but they have not been used in the smaller 1,000 pound and less of thrust category. And the reason can be seen in this chart. On the right-hand side, you see that the blisk is integrally made with the rotor and the airfoils together, which makes it sometimes hard to coat those airfoils because line of sight to every section of the airfoil is not really feasible. On the left, you see an aircraft engine, which is assembled as airfoils put into the rotor after those airfoils are coated. Such an assembly is not practical in the small engines because the leakage generated with the assembly is too much in comparison to the flow going through the engine. We're going to optimize the coating process for this small size class, and we're looking at air plasma spray as well as electron beam physical vapor deposition, or EBPVD. We do have a beachhead customer identified. We're planning to work out all the kinks, and we think that there's a large opportunity to follow, particularly, as I mentioned, in the military unmanned space. There's military and commercial opportunities. Also, we do have an unusual technology that can see under coatings if there are cracks or not, which will put us in a very good position to do repairs on coated commercial parts. We can strip and recoat if it's needed, but if it's not needed, we won't have to spend that money. Also, we have contacts at the Department of Energy, and a coating and a cooled and coated blisk in the back of those units could be very helpful to increase the power output. Why Core Parts? Core Parts is around since 2015, and we provide about 100 different part numbers for our customers in the aftermarket space. We are known for high quality, and we are very experienced with coatings as well as cooling. And it will take cooling expertise to understand the nature of these thermal barrier coatings, particularly if we don't get full coverage on every part of the airfoils. We also have a proven quality control system, which we'll be putting to work for this project. This is our team. The principal investigator is Jim Downs, who has 35 to 40 years of airfoil cooling experience. He's quite well known, and many publications have been written by him. And Ray Sinatra is a specialist in coatings. He has 8 patents in coatings, as well as publications, and is quite well known. Tab Heffernan is an expert in design for manufacturing. Larry Batchelor runs our aftermarket commercial business. And I have quite a bit of experience with business growth, having started Florida Turbine Technologies 20 years ago that sold last year. We're going to be working with KTT as a teammate, and John Appleby is also on the team as a teammate, and he has quite a background in coatings as well. Thank you so much for your time. We look forward to the project.